components of cylinder heat exchanger. Okay, so I think we have almost covered all the components, major components of cylinder heat exchanger, and the comparison of different types of cylinder heat exchangers also we have discussed, correct? Fixed tube seat, U-tube, floating head, those things. Okay, so what are all the factors that is to be considered while selecting the types of heat exchanger? Okay, that is maintenance, cleaning, then thermal expansion, then size of the cell, then heat transfer coefficient, because the heat transfer coefficient may be suffered by this by passing area. Okay, then fixed cost of the exchanger, the number of tube passes. Sometimes this number of tube passes can be selected based on the diameter of the cell. Okay, so if it is more than 1200 mm, such cases we have to go for more number of passes, 8 to 12 passes, like that. Okay, the nature of the plant. Okay, so these are all the things that we have to consider. Then today we will see the complete picture of cylinder heat exchanger. Okay. Design of cylinder heat exchanger, design picture of cylinder heat exchanger. Okay. So with respect to design of cylinder heat exchanger, last class I told we have many methods. Okay, so the very basic method before proposed in 1960s, before 1960s, they developed this design methods without considering this bypass and leakage. So in exchanger we have so many streams. Ideal cases we can see this ideal cross flow and ideal axial flow. Okay, but practically that is not the case, as we have many bypass streams and leakage streams. Okay, so what is this Kern in 1950 and this Donahue in 1955? They proposed these design methods based on bulk flow methods, that is actual cross flow and actual ideal flow. By considering this, they developed the design methods for cylinder heat exchanger. Later on, what happened when compare the experimental value with the calculated value by these methods, the deviations were more. So what they have done more research on these cases. They found that cell side estimation of heat transfer coefficient and pressure drop deviates more as per Kern method with the experimental values. Okay. So they looked upon the reasons and identified that the stream analysis is must in the especially in cell side, because there were so many clearances, that is tube hole to tubes, cell bundle to cell, then you can say pass partition plates. Okay, then different streams, no, A stream, then B stream, okay, then C stream, that is a bundle to cell, then E stream, okay, that is a baffle to cell. Okay, so these are all different streams, and F stream due to pass partition plates. Okay, so these bypass stream and leakage streams plays major role. So it is necessary to account the correction factor to account these streams. Okay, contribution of these streams are whether it may be positive or negative on cell side heat transfer coefficient pressure drop. Okay. So that's the model proposed by Tinker. It is iterative process, tedious process. Later it was modified by so many people. Finally, now we are following this method called Bell-Delaware method for cylinder heat exchanger design. Okay. So anyway, we start with the Kern method. That is the very basic method. So it will give an idea how we can do the cylinder heat exchanger. Then we move to Bell-Delaware method. Okay.
Sir, are you sharing any PowerPoint, sir?
Yeah. Today, now I am going to share. Till now I didn't share any PowerPoints. Just I briefed what I have taught in last class. Okay.
Okay, sir. Okay, sir. Thank you, sir.
So now I am going to Are you getting my slides?
So yes, sir, slides are visible.
Yeah. Okay. So we'll go by step. The very first step in salary heat exchanger design is we have to calculate the heat duty. So here we have three different cases. Okay. So here with phase change and without phase change. So without phase change means for heating or cooling or no phase change, you can use this equation Q or phi whatever may be, that is equal to m dot Cp delta T, where delta T is the effective temperature difference in the exchange. Okay. Then this m dot is a mass flow rate and Cp is the specific heat capacity. So the objective of the exchanger may be heating or cooling. So if it is cooling means the hot stream has to be brought down to the required temperature. Heating means the cold stream temperature has to be raised to the target temperature. Okay. So we can calculate the heat duty based on the objective. Okay. Or if it is condensation with subcooling, such cases, in addition to this sensible heat, we can take in addition to the sensible heat, we have to account this latent heat also, m lambda. Okay, so this is for condensation with subcooling. If you don't have subcooling, this term becomes 0. Okay, so you have to use m lambda into, you have to multiply by this factor 0.05 to account the losses. If it is reboilers, okay, this condensation and reboilers are heat transfer with phase change. Okay, so this phi is equal to m lambda. This is mass, vaporized mass. This is condensate mass. Okay, so lambda is latent heat. It has to be multiplied by 1.05, that is 1 plus 0.5% to account the losses. Okay, losses in terms of radiation losses or sometimes convection losses. Okay, many losses are there. Okay, so we have to account those losses here. Okay, so once this heat duty is being calculated, we have to identify the suitable heating medium or cooling medium. Heating medium means if your exchanger is designed for cooling, then you have to identify the cooling medium, because cooling means the hot fluid temperature has to be brought down. Heating means cold fluid, that is temperature has to be brought up. So you have to identify the heating medium. So we have different types of heating medium like saturated steam, then thermic oil, Doutham E. These are all organic fluids. Okay. Then you can say Doutham A, because these two fluids are modeled by Dow chemicals, so it's called Doutham chemicals. Thermic fluid developed by Dow is called Doutham. Doutham is nothing but ortho dichlorobenzene. This is nothing but ortho dichlorobenzene. Okay, but this here Doutham A is also an organic fluid. Okay, normally it has very high heat stability. Okay, and it is an eutectic mixture. So it is an eutectic mixture, which is a mixture of diphenyl and diphenyl oxide. Diphenyl and diphenyl oxide. This is the combination of Doutham A. The percentage will vary. Diphenyl will be around 27%. diphenyl oxide will be around 73%. So this is like a eutectic mixture. Okay. So the and the applicability of these cases, these things will be in this temperature range. Okay. There are molten salt you can use, sodium, potassium alloys, flue gas, then electric heating. So electric heating normally used above 1100 degrees centigrade. Normally electric heating will be used for heating purpose. This flue gas or hot air. Okay, so this is a recovery of waste heat from the flue gas that is used in the range 750 to 1100 degrees centigrade. Okay, the sodium potassium alloys normally sorry 590 to 750 degrees centigrade. This molten salt is 400 to 590 degrees centigrade. This Dautham E and Dautham A, that is Dautham A is 300 to 400, Dautham E is 180 degrees centigrade. So sorry, this saturated steam you can go up to 180 degrees centigrade, because the steam, if you use steam, saturated steam as the heating medium, the heat transfer coefficient of this steam will be around 5000 to 6000 watt per meter square degree centigrade. Very high heat transfer. The resistance is very less. Why? The steam is steam condensation is a very good example for drop-wise condensation. Okay, so you might have studied different types of condensation, film-wise condensation and drop-wise condensation in the heat transfer subject. Okay, anyway, when we discuss the design of condensers, I brief out or I summarize the things that you have studied in heat transfer so that it will be easy for you. Okay, so but we will not use this superheated steam. Saturated steam you can use. Superheated steam means normally what will happen? It has high temperature steam above and it this in addition to latent heat, it may have sensible heat also. Okay, so the sensible heat means what happened? This heat transfer coefficient or Cp value of this steam will be very very low. So such a cases the resistance, or you can say the heat transfer coefficient will be in lower side. Okay, so most of the times we will go for this saturated steam as the heating medium, when the temperature range is around 100 to 180 degrees centigrade. Okay, if it goes more than 180 degrees centigrade, the saturated steam, using saturated steam is not the preferable one, as the cost of the steam at higher temperatures will increase. That's why you have a high pressure steam, medium pressure steam, low pressure steam. Normally, whenever you increase the pressure of the steam, the quality of the steam will increase. In turn, the cost of the steam will also increase. So operating cost will increase. Okay, so steam above 180 degrees centigrade is not preferred. That's why, otherwise your utility cost will be more. Okay, so that's the idea of pinch. Pinch is we have to recover the maximum possible heat from the process streams. That is pinch technology. Okay, so if you increase the possible heat transfer from the process streams, what happened? Your utility requirements will come down. Even though your utility requirements will come down, we have to decide at what temperature this utility has to be introduced. That matters. Okay, so for above 180 degrees centigrade, we will not go for steam as the heating medium normally. Okay, if required, you can go. Okay, so otherwise this thermic fluid is normally used, or you can say hot oil. Hot oil or thermic fluid, the range is 180 to 300 degrees centigrade. Okay, so these are all different heating mediums. Based on the temperature range or heat transfer coefficient or cost, we can select that heating medium. Then cooling medium is different types of cooling mediums. Again, I can say based on the temperature range. Here you have brines, then chilled water, cooling water, oil, air. Okay, so air is available at atmospheric temperature. So we cannot go the temperature greater than 60 degrees centigrade. We cannot use air as the cooling medium. Okay, so brines is you have different examples: ethanol water solution, methanol water solution, ethylene glycol, aqueous solution of calcium chloride. So these are all organics, correct? So these are all inorganics. Aqueous solution of calcium chloride, aqueous solution of sodium chloride. Okay, then you can say combination of this methylene chloride, trichloromethylene, then trichlorofluoromethane. So whenever the temperature range is below 0 degree centigrade, okay, such a cases we will go for these type of things, brines. Okay, the recommended to use for temperature range is from 8 degree centigrade to minus 30 degrees centigrade to 8 degree centigrade. So you can use aqueous solutions up to less than 8 degree centigrade. You can go for these things. Okay. Otherwise, if it is less than 0 degree centigrade, such a cases you can go for this type of methylene chloride, trichloroethylene, and trichloride. Then chilled water, you can go for the operating range 5 to 12 degree centigrade, and cooling water you have to go for 30 to 60 degree centigrade. Okay, so cooling water means normal water available in the atmosphere. So you cannot, the range, upper range indicates that you cannot heat these things above this temperature. Otherwise, what will happen? This cooling medium will extract the heat from the hot fluid, no? So again we have to reuse this. So such a cases the cost will be more. Cooling water means you can use cooling towers to cool it to the dew point, or you can say adiabatic saturation temperature. Okay, okay. Using cooling towers, you might have studied in equilibrium stage operation or mass transfer 1. Okay, anyway we will see later simultaneous heat and mass transfer operation. Okay, then oil you can use minus 1 to 3 16 degree centigrade. Some cases, in the previous case I saw no this oil. So oil will be first in agitated vessel. If it is exothermic reaction, oil can be used. So what will happen? This oil will extract the heat. Then it can be released to some other point. Again, it can be used as a cooling medium. So this hot oil can be used as both heating medium and also cooling medium. Okay, that's the idea. Okay, so these are all different cooling mediums that can be selected based on this temperature range mainly, and heat transfer coefficient, and the cost. Okay, this is the idea. Okay, and some cases this minimum temperature is 5 degrees centigrade, no, chilled water. It should not go below 5 degrees centigrade. Correct, chilled water. So the range you can fix it based on the available delta T. Okay, so in the case of process fluid, heat recovery from process fluid, you should have at least minimum 20 degrees centigrade. Okay, so 10 to 20 degrees centigrade. Such a cases, what happened? This 5 degrees centigrade, that is the inlet temperature of the chilled water, plus delta T is 15 degrees centigrade or 10 degrees centigrade or 20 degrees centigrade. So the outlet temperature you can approximately you can fix. Okay, based on the specific heat of the other side, hot fluid, those things. Okay, so that is necessary that you have to fix the delta T, minimum driving force required for heat transfer in cell side or tube side. Based on that, you can fix the temperature range of these things. Okay. Then the third point is fluid allocation. So fluid allocation we have to account for different things. Okay, the 7 factors we have to account. So corrosion, fouling, these are all 2 important things. So whenever the fluid is corrosive or fouling in nature, those fluids will be used in tube side. Why? The cost of the cell is high, and even if you have any problem when you use this fouling fluids or corrosive fluids in tubes, you can immediately isolate the particular tube after identification. You can immediately isolate the tube by using by blinding its inlet and outlet. Okay, just plugging, just use plugs, you can isolate the tubes. Then you can continue the process. But that is not the case if you use these fluids in cell side. If you have any problem with the cell, then changing the cell is a very big issue. So this corrosive and fouling fluids normally will be used in tube side. Then fluid temperature, you have to see the very high fluid temperatures normally used in tube side, because if you use the high temperature fluid in cell side, then you have to change the material of construction, and you have to provide suitable insulation, lagging you have to provide. Okay, this will increase the capital cost of the exchanger. So high temperature fluids normally used in tube side. So then operating pressure, Again, operating pressure. Yesterday I told no when we discussed about tube sheet thickness. I gave one equation that is T equal to Fg root of P by 4F. Correct. So this P is the design pressure. Okay. So this design pressure increases. What will happen? Your thickness will increase. Okay, so operating pressure based on the operating pressure. So if your thickness of the cell increases, the cost of the cell increases. Okay, so what we can do, the high pressure fluids normally can be used in tube sites. Okay, then fluid rates and viscosity, fluid rates, that is steam flow rate, both are same. Okay, so this both are same. So high flow rates, I told no, we can go for this split flow, divided flow. Such cases, if you have very high flow rates, we can go for cell side. Okay, because the cell side, the critical Reynolds number for turbulent flow will be very small. That is around 200. But in the case of tube flow, the critical Reynolds number you know. So the Reynolds number greater than 2000, you can say it is sorry, less than 2000, you can say it is laminar. So or 2100. Or if you say more than 4000, the flow is turbulent. So this 2100 to 4000 is transition. Correct. So the flow rates are very high, and if the viscosity, that is important factor, viscosity is very high, those fluids normally be used in cell side. Okay, this is the fluid allocation. Once you selected, calculate the heat duty, you have to identify the suitable medium. Then you have to allocate the heating medium and cooling medium, or process fluid or service fluid in cell side or tube side. Fluid allocation has to be done. Okay. Then other important factors that you have to consider is velocity, cell and tube fluid velocities. Okay. So normally, if velocity is more, then what happens? Your heat transfer coefficient increases, and also the pressure drop will also increase. Okay. So we have some certain thumb rule to select the liquid velocity. So if you allocate the high viscous fluid in tube side, what will happen? It will not reach the required velocity, because this is highly viscous, no? So you have more resistance to flow. Then what would be the problem? The velocity will be in lower side. So normally these high viscous fluids will be allocated in cell side. So for liquids, the permissible or desirable range of velocity would be normally 1 to 2 meters per second, and maximum you can go up to 4 meters per second. Okay. In water, if you use water, generally you can go 1 to 3 meters per second. The operating range you can select 1.5 to 2.5 meters. So once you calculate the mass flow rate in tube side, and calculating, fixing the dimensions of the tubes, you can calculate the velocity using cross-sectional area. Then you can check. So if you see the velocity will be in lower side, what you should do? You have to increase the number of passes. If it is in higher side, you have to reduce the number of passes. So this velocity of the fluid will give a rough idea to optimize the number of passes. Okay. Cell side normally the velocity range of liquids will be around 0.3 to 1 meters per second. Okay. Otherwise, if you go beyond this, it will create, develop more pressure drop. Okay. In vapor side, the velocity will be function of pressure and density. For high molecular materials, in some of the classes I told, when you use at atmospheric pressure, the velocity range will be around 10 to 30 meters per second, sometimes 10 to 20 meters per second. Okay. So if we increase the pressure, what will happen? It is like a liquid, correct? So the velocity range will be around 5 to 10 meters per second. At vacuum operation, the velocity will be in the higher side, 50 to 70 meters per second. This is the idea about your tube side velocity. Then you have to see the stream temperature. So here you have to show the closer approach. Approach means, you know, so this is your hot fluid and cold fluid. Okay. So this one will say about approach. Whenever the approach is very small, what happens? It will reflect on your heat transfer area. The heat transfer area will increase. That is approach. So this is range. This terminal temperature, the difference the outlet temperature of the hot fluid and then inlet temperature of cold fluid, the difference between these two is called approach, especially in counter current flow. Okay, so the to approach is very closer, your driving force will be less, your heat transfer area will be more. So you have to do this optimum based on the economic analysis, that you have to do the cost analysis, like capital cost and operating cost that you have to do. Then you can identify the temperature range, or you can accordingly you can modify. Okay, then pressure drop means in exchanger it can be from a few millibars to several bars. Okay, so you have to look up these things. Okay, for liquids normally the permissible range is 10 to 12 psi, I said, correct? So if the liquid viscosity is less than 1 millinewton second per meter square, or you can say 1 centipoise, okay, less than 1 centipoise, the permissible limit is 35 kilonewton per meter square, or you can say 5 psi or 6 psi. So the 1 to 10 Cp centipoise, the allowable limit is 50 to 70 kilonewton per meter square. That is around 10 to 12 psi. Okay. So if it is gas and vapors, then it depends on the pressure. Your permissible pressure drop depends on your pressure conditions. For 1 to 2 bar, normally it will be 0.5 times of gauge pressure. For above 10 bar, it is 0.1 times of operating pressure. Then for medium vacuum, it will be 0.1 times of absolute pressure. Then for high vacuum, it will be normally 0.4 to 0.8 kilonewton per meter square. So you can because once we did thermal design, we will do the hydraulic design, we will estimate the pressure drop. If the pressure drops are greater than a permissible limit, such cases again you have to rewrite your design process. Okay. So the third step is that once you know the heat duty, okay, then you have to make the energy balance. So based on the energy balance, because if it is heating medium or cooling medium, whatever you selected for the process fluid, okay, the inlet temperature is known, the outlet temperature is unknown. So the outlet temperature can be calculated based on this heat duty balance, or you can say the energy balance. Or if you know the temperature conditions, you can calculate the mass flow rate, because these two things are unknown here, correct? So mass flow rate, or it may be outlet temperature. Okay, so you have to do this equation energy balance. For example, in the case of condenser, m lambda is equal to mCp delta T. This is the heat gain, heat loss by the vapor. This is the heat gain by the cooling medium. Okay, so you can calculate this one or this by fixing the any one, because you have two unknowns, 1, 2. So the Cp you can calculate, the inlet temperature is known. Okay. So by energy balance, you can do the flow rate or temperature. That is the third step. Then fifth step is we have to find out the mean temperature difference. Okay. So in double pipe exchanger, we didn't discuss about this factor called LMTD correction factor. So because in salinity heat exchanger, we have more than one tube passes. So 1 exchanger means you can use this FT becomes 1, correct? For 1 exchanger, this LMTD correction factor becomes 1, because you will get pure co-current or counter current flow. But in the case of 1 2 passes, what will happen? If you see the temperature profile, if your hot fluid in cell side, cold fluid in tube side, or whatever may be, the temperature, if it is 2 passes, means it would be like this, correct? So this would be the temperature profile. Here you can say this is temperature, this is length of the exchanger. Okay, this is inlet point, this is out. Okay. So with respect to first pass, it's counter current. With respect to other case, it is a co-current. So the heat exchanger will experience both co-current flow and counter current flow. Such a cases, we have to account this. We have to calculate this. We have to correct this delta T m. Okay, this is a delta T LM, logarithmic mean temperature difference, or AMTD has to be corrected using this FT LMTD. So this LMTD correction factor is normally function of two factors, R and S. One is called capacity ratio, another one is effectiveness of the exchanger. Okay, So this T1 minus T2 by T2 minus T1. So normally smaller T is used for cold fluid, capital T is used for hot fluid. One means inlet, two means outlet. Okay. So here this is the effectiveness. How you can say effectiveness? This is your cold fluid, correct? This is your cold fluid profile. This is your hot fluid profile. So you can say this is T1 inlet temperature. This is T2 outlet temperature. Here this is T1 inlet temperature. This is T2 outlet temperature. It goes like this. Okay. So this is the heat gain or temperature rise of the cold fluid. That is the possible. That is the temperature rise. What is the maximum possible? This T2 minus T1. So this T2, sorry, you can say this is the T1, correct? T1 minus T1. Okay, this is the maximum temperature difference in the exchanger. That is the maximum possible temperature difference that can be applied in the exchanger. But practically that is not the case. So that's why we are taking this is the maximum possible temperature difference. So this is called effectiveness. This is actual temperature drop, okay, or temperature rise of the cold fluid. This is the maximum possible temperature drop. That is hot fluid inlet temperature minus cold fluid inlet temperature. So using these two factors, we can calculate the LMTD correction factor. Okay. So here you see this LMTD correction factor is always 1, as I said. So sometimes what will happen? This is called temperature crosser. This is not desirable. Okay. So using R and S value, you can calculate this LMTD correction factor for 1 to exchanger. This is one or 1 and even number of tube passes. Okay. So this is this derivation, I think similar to your LMTD one. Okay. So anyway, that's not our objective. Or you can use DQ kern. Refer DQ kern how the equation is being arrived to calculate the FT values. Okay. So this is analytical expression to calculate the LMTD correction factor, and also we have so many charts like this. Okay. So here this chart is for temperature correction factor for 1 cell pass and 2 tube passes or more even tube passes. Here the x-axis is S, your y-axis is FT, your R value is the parameter. Here you can see the disadvantage of this chart is that in this case at a very higher value of these things. So your R value increases like this, no? Correct? Your S value increases. The maximum possible is 1. Sorry. Okay, here you have FT, the maximum value will be 1. Okay, your R value goes like this. R is capacity ratio, S is your effectiveness of the exchange. Okay, so what will happen whenever your R value is less? Okay, then at higher values of S, here you can see the trend. So here the prediction of LMTD correction factor using chart at above 0.9, because this is almost linear, correct? So this is very few cases. Here this is the drastic changes. Here 0.5 to, for example, this case when R equal to 0.1 and for S equal to 0.5 to 0.9, the variation is drastic. Okay, the variation is drastic. Okay, so the prediction is sometimes difficult in these cases, but anyway, this will give a better idea. So what is the limitation for these values? So FT is 0.75. So FT should be 0.75, steep slopes in chart. After that, what happened? There is no unchange. There is no change. There is no change in the value of your FT value, even though at constant value of S, what happens? It's almost same, correct? Here also you can see this is linear portion, this is non-linear portion. So here the variations are very less, but drastic changes in FT is observed. Okay, so what is the limitation? Where we have to stop the FT? So FT always preferred should be more than 0.75. Okay, so FT less than or equal to 0.75, you can see this steep changes in the, that is almost vertical. Okay, so if you see the slope dy by dx, the variation is very, very small. Okay, high. Okay. So this is the reason bypassing of streams would be the reason for FT, because in these cases what will happen, the temperature approach or temperature cross is possible. Okay, so this is your LMDD correction factor chart for 1-2 process. So here we have different cases. So I told no. So if the approach is very close, your heat transfer area will increase. What does that mean? Your temperature drop will come down. Okay. So here your approach is high, correct? This is your outlet temperature. This is your outlet temperature of the hot fluid. So this is your temperature approach, correct? So what happened? This is in if you calculate for these conditions, the LMDD correction factor value will be around 0.9. Okay. So if you change this, so here what we observe, the cold fluid outlet temperature is more than the hot fluid outlet temperature. So what happens? The temperature cross. This is called temperature cross. Okay. So here we have a small temperature cross. Then what happened? Here your LMDD value has brought down to 0.75. Still, if you go higher temperature cross, what happens? This goes like this. So your LMDD correction factor goes to 0.5. So that's not permissible. In such a cases, what will happen? Your LMDD area will increase drastically. Okay. So approach is small means heat transfer area will increase. If the temperature cross is there, your area is completely more than this case. Okay. So we have to fix the LMDD value. Okay. So the normally preferred value is 0.75. Okay. LMDD value normally preferred is 0.75. Or you can go more than that. Accordingly, you can tune the number of passes to get the favorable temperature approach. So that's the point. Okay. Then fifth step is that you have to estimate the overall heat transfer coefficient. Okay, for different combinations. Already we have discussed in double pipe heat exchanger. For different combinations, you can select the range. For example, water, the value will be around 800 to 1400 watt per meter square degree centigrade. You can select around 1000 or 1200. Okay. Similarly, for different combinations, organic solvent water, light oil water, heavy oil water, water brine, gas brine, gas. You see, the overall heat transfer coefficient will be in the lower side, 10 to 50 watt per meter square. So gas exchanger, the heat transfer area will be, because the resistance is higher, so you have to provide extended surface. So that's the idea. Okay, so you have to provide more heat transfer area so that you can increase the you can get better performance in the exchanger. Okay, so this gas brine, you see the temperature, this overall heat transfer coefficient will be in the lower side. The order of magnitude is small whenever with respect to overall heat transfer coefficient when we handle this gas. Okay, naphtha water, then lube oil, these things, then kerosene water. See, kerosene water, it will be 1150 to 300. Okay, so different combinations are there. If it is condensers, again you see one side you have vapor, another side you have the water or other cooling mediums like brines. Okay. So steam, you see, when you use steam water, the range is greater, correct? 5000 watt per meter square, which means the heat transfer resistance offered by the steam is lower side. Similarly, vaporizers, most of the cases we are taking steam as the heating medium. Okay, so these are all different cases. So you can see whenever you are using steam, the heat transfer coefficient will be in higher side. So here this overall, here it would be around 5000 to 6000 watt per meter square. Okay, but if you see this value is 1500 or 2000 watt per meter square degree, which means that this light organic or heavy organic, these things offer more resistance than even if you use high heat transfer coefficient fluid in other side. Okay, so you have to select the value of U based on these combinations. Okay, then estimation of heat transfer area based on the U assumed. So heat duty divided by U delta T LMD. This is corrected by LMDD. Then you will get the heat transfer area. From the area, you can calculate that is a provisional area or provided area, you can say actual area, whatever may be. Okay, that is equal to NT by D naught R. Okay, now here we have to decide the tube side passes, cell side passes, tube arrangement, type of heat exchanger. Okay, everything you have to decide. And tube diameter, how it is being arranged, triangular pitch or square pitch, everything you have. Then finally you have to find the cell diameter. So cell diameter, as we discussed, you can use three different methods: analytical equation, tube sheet layout diagram, or tube count table. So using this, you can calculate the cell diameter. Okay. Then we have to calculate the tube side heat transfer coefficient. Once it is being done up to 7th step, tentatively we have decided the size of the exchanger. Sizing is being done. Correct. Now we have to rate the exchanger, whether this exchanger is suitable for the required temperature conditions. Okay. So next thing is that we have to calculate the tube side heat transfer coefficient. Here you can use Cedertate equation. Okay. That is, we have discussed in double pipe heat exchanger. You can use the same equation here. The condition is that Reynolds number should be less than 2000, or if you get the value of the Nusselt number less than 0.35, then you can take the Nusselt number 3.5. Then the L by D ratio should be less than 500. These are all the conditions to use the Cedertate equation. So this is viscosity correction factor. Okay. If the Reynolds number is greater than 4000, you have to use this Cedertate equation for turbulent flow, or if you assume this equal to 1, then it's called detectable equation. That is constant into Reynolds number power 8, Prandtl number power 0.33. So the terminologies you know: L is length of the tube, okay. Then K is thermal conductivity, Cp is specific heat, mu is viscosity of the fluid at bulk fluid temperature, UW is the viscosity of the fluid at tube wall temperature. Okay. The value of C is 0.2021 for gases, 0.023 for non-viscous liquids, 0.027 for viscous liquid. Okay. So the Reynolds number can be dV rho by mu or dGt by mu. Okay. Different forms we have discussed for Reynolds number. So this GT, if you know the tube side mass velocity, then you can use this Reynolds number. If you know the GT, this AT is nothing but the cross-sectional area, that is tube side flow area. Okay, so number of tubes into pi by 4 d square will give the total flow area of the exchanger, tube side flow area exchanger. If you divide it by number of passes, you will get tube side flow area. Okay, 2 passes means the flow area will be half of this. Okay, NT by 2, number of passes will be 2. Okay, sometimes what will happen? If the heat transfer coefficient falls between 2000 and 4000, you have to use both the equations, and the lesser values you have to consider. Okay, lesser value means more resistance. So we are conservative and you are using the heat transfer coefficient. So you have to take the lesser values. Okay, or sometimes different equations are proposed to calculate the heat transfer coefficient. One is in terms of Stanton's number, Reynolds number, and Prandtl's number. Normally, this equation is used for Reynolds number greater than 10,000. Okay, so your Stanton number is nothing but Nusselt number by you can say Peclet number. This is nothing but Peclet number, correct? So Prandtl's number into Reynolds number is Peclet number. Okay, Peclet number. So Nusselt by Peclet number is called Stanton number. That is H by rho u Cp. H by rho u Cp. Okay. The constant E is again expressed in terms of Prandtl number. This equation is proposed by Butterworth. Okay. Or you can use the chart to calculate the heat transfer coefficient. So you know the Reynolds number, so you know the heat transfer factor. So this is the equation normally used, correct? Or as per current, you can use this equation. Okay. So here you are having this small JH, correct? So JH is equal to Stanton number, Prandtl number power 0.67 into your mu by mu W power minus 0.14. So Stanton number you know, that is Nusselt number by Reynolds number. So you take the Cedertate equation, divide both the sides by Reynolds number and Prandtl number, you will get this equation. Okay, you will get this type of equation. So JH you have to calculate, that is HD by K is equal to JH, Reynolds number, Prandtl number power 0.3, and viscosity. Here you have to see the difference. This is plus 1/4, this is minus 1. Okay. So this is the way you can use this chart to find out the heat transfer coefficient. So here up to laminar flow, this is 2000 now. So up to this is laminar flow and it is function of different L by D. Okay, as per current you can use this JH, this is capital H, this is small h. Okay, so that is Nusselt number, Prandtl number power minus 1 by 3, mu by mu W power minus 0.14. This is the. Now you can relate this JH with this, the current JH with this JH. So JH is equal to JH of Reynolds number. Okay, this. Sometimes if you use water, you can use for water you will have specific equations. So if you use Cped or Dittus-Boulder equation to calculate the heat transfer coefficient for water, the deviations are more. Okay, or it would be around 25% to 30% deviations. So Eagle and Ferguson proposed an equation especially for water to predict the heat transfer coefficient. That is 4200, similar to your Cp value. Okay, 1.35 plus 0.02 T, where T is the water temperature, average temperature you can take, Ut power 0.8 divided by ID of the pipe power 0.2. So you have to use the units, dA in mm, Ut is in meter per second, okay, temperature in degree centigrade. Okay, so then only you will get Hi in watt per meter square Kelvin. Okay, so this is the way you can calculate the heat transfer coefficient. So how to calculate the pressure drop? So when you go to estimation of pressure drop, we have two different losses. One is major loss, another one is minor loss. So major losses normally calculated using this equation for pipe flow. Okay. Okay. So if this is for normally for isothermal flow, because in this equation, if you compare these two equations, here you don't have this correction factor, viscosity correction factor in this equation. Why? This is for isothermal flow, so your mu and mu W will becomes 1 in this case. So if there is isothermal flow, non-isothermal flow, you have to account this. So the value of M minus M is 0.25 for laminar flow, 0.14 for turbulent. So you can calculate this major loss, that is pressure drop due to pipe flow. So you have Reynolds number and friction factor. So you can calculate from chart also. So JF you can calculate, substitute here. L dash is effective length. Effective length means tube length minus 2 times of tube sheet thickness, because we are inserting the tubes in tube sheet, no? So that portion we have to subtract. Okay, so normally some people will not use, because the tube sheet thickness is very small, then it is not necessary to correct your length. Okay, otherwise you have to go for effective length. This is tube ID, then rho ut square by 2, so that you can calculate the delta P. This is for major loss. How to calculate the minor loss? So minor loss, if you see this exchanger, major loss you can calculate the loss pressure drop due to bulk flow or flow through the tubes. Okay, due to skin friction. Okay, but minor loss here, if you see, if this is the tube side fluid inlet, this is tube side fluid outlet. What happened? Here this diameter and this diameter is different, so we have sudden expansion. So then this head to tube, then sudden contraction. Okay, then tube to this head, sudden expansion, then head to tube, sudden contraction, then tube to head, sudden expansion. Okay, so the exchanger is exposed to 2 contractions and 2 expansions and 1 reverse flow. So if you go for 2 tube passes, what will happen? The tube side fluid is exposed to 2 contractions, 2 expansions and 1 flow reversals. So different people worked on these things. Okay, so Kern proposed to minor losses in terms of velocity head. Momentum transfer lab minor loss estimation, you might have studied that you can express the minor loss in terms of velocity heads or this pipe equivalent diameter. Okay, so these 3 are like straight pipe equivalent diameter, because here L is in the equations, previous equation, this L is replaced by in terms of diameter. So L dash you can use 300 times of D or 200 times of D or 67 times of D. Okay, so different methods are there to account your minor losses. Okay, so here you have Kern method. He accounted 4 velocity heads. Frank proposed 2.5 heads. So he has some rationale to express these minor losses. So what he has done, contraction he used 0.5 velocity heads. For expansion he used 1 velocity head. for flow reversal, he approximated 1.5 times of velocity heads. So what happens? So this is for 2 passes, correct? 2 times of this is 1, 1 plus 2, 3, 3 plus 1.5. So 4.5 velocity heads is used to express your minor losses per 2 pass. Okay, so approximately 2.5. So finally they approximated 2.5 times per pass. So what happens? The equation is modified like this. So your total loss will be this is the major loss and to account the minor loss. Okay. So in addition to that, we have another loss like nozzle pressure drop. Okay, our inlet and outlet nozzles we have. So for inlet you have 1 velocity head and outlet you have account 0.5 velocity. Okay. So do you need a break at this point? 5 minutes, 5 to 10 minutes. Hello.
Sir, okay,
Yes.
sir. 5 minutes.
Yeah.
We'll
So
resume at
we will come back
10:30, sir.
again after 5 minutes. Okay. So we will continue after 5 minutes. Okay.
Yes.
Okay. Thank you. Thank you. Hello. Madam, madam. Class madam. அதான் மேடம் அந்த ரிசிப்ட் அனுப்பிட்டுங்க மேடம். அது அதோட தான் கொடுத்து டைரக்ட் ஆஃபீஸ்க்கு. இல்லை மேடம் அந்த அட்வான்ஸ் ஃபார்மு அந்த அந்த அப்ரூவல் போட்ட மேடம் சைன் பண்ணிருந்தாங்க. டைரக்ட் ஆஃபீஸில் கொடுத்து இங்கே ரெஜிஸ்டர் ஆஃபீஸில் கொடுக்க சொல்லிங்க மேடம். நேற்றே கொடுத்துட்டேன் மேடம். நேற்று சாயங்காலம் கொடுத்துட்டேன் மேடம். கொடுக்குறேன்னு சொல்லுங்க. இல்லை ஏதாவது ஃபோட்டோ எடுத்து ஆக்கணுமா சார்? சரி. ஓகே மேடம். ஓகே. அதுதான் மேடம். அதுதான் அனுப்பிடுவோம். நேற்று அப்ரூவ் பண்ணாங்க மேடம். மண்டே போகணும். இல்லை 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 மேடம். மேம் ஹார்ட் காப்பி தான். ஹார்ட் காப்பி தான். தேங்க்யூ. தேங்க்யூ. Shall we start?
Sir, yes, sir. We can start, sir.
Yeah. So this is the way to calculate the pressure drop in tube side. We have to calculate the major loss and minor loss. So major loss is accounted using this NP into 8JF L by dA into mu by mu W power minus m. Okay. So this 2.5 NP into 2.5. This is the velocity head. For per pass in for minor loss. Okay, so this is the way to calculate the pressure. So this is the simplest part, whatever we have discussed in double pipe heat exchanger. Similarly, in cell side, the calculation is a bit different, whatever we have done in double pipe heat exchanger. Okay, so cell side, this is the method is Kern method. As I said earlier, it is bulk flow method. Okay, but the prediction of heat transfer coefficient and pressure drop by Kern method is less satisfactory. Okay, because Kern didn't do the stream analysis. He didn't account this bypass and leakage streams. Okay, so and also he used this hypothetical cell diameter and cell velocity. So what he has assumed is cross flow, the maximum flow. If this is your cell ID, so this is the flow. Okay. So he calculated the velocity based on the cell diameter. Okay. So, but actually what happened? The cross-sectional area for flow will vary with the diameter. So here you may have different cross-sectional area. So if the if you calculate the flow area based on this value, the cross-sectional area is different. The cross-sectional area is maximum when you use the diameter. Okay, but it will vary with the diameter, correct? So cell velocity is affected by all these things, cell diameter. So continuously it's flowing like this cross flow, no? So what happens? The velocity is continuously changing inside the exchanger. Okay, so the cell velocity is affected by these things: cell diameter, clearance between the tubes, okay, and tube pitch, then baffle spacing. All these things are matters when you calculate the cell velocity. So, but what Kern did, he calculated the velocity using this flow area AS. So, cell side mass velocity GS is equal to WS by AS. So, the really linear velocity US is equal to GS by rho. Okay, but how he calculated this bundle cross sectional area per flow based on this DS. Okay, so based on this DS, this is the cross flow area, where C is the clearance, that is PT minus D naught. So LB is the baffle spacing. Okay, length of the flow area. For example, if this is your view, you take the view of your exchanger, so your tubes will be like this, correct? These are all the tubes. This is your diameter. So this is your cell. Okay, so you have many tubes are like this. So if you calculate this, what happened? This is your tube, no? This is your tubes. If you zoom this portion, so you have two tubes, correct? It goes like this. Okay, so this is your clearance, PT by D naught. So this is your DS. You have to calculate this DS by PT, you know. That will give the number of tubes, correct? DS by PT, you know the number of tubes. L is the baffle spacing. So what is the flow area? This is the area available for flow. So this is your tubes. If you see from the top, so this is the L, correct? So this is your L. So this DS by PT is your this thing, correct? DS by PT. This is DS by PT, number of tube rows. So the gap, that is the clearance. That is you can say PT minus D naught. That is the gap available for the flow. This is the flow area available for the cell side fluid. So that's why we are calculating this PT DS by PT, number of tubes, okay, into PT minus T naught times into LB, length of the things. So this is the area available for flow. Okay, so like this you have to calculate the cross-sectional area, bundle cross-sectional area for flow, that is calculated based on maximum. It is ds based on this diameter. Okay, so the width of the flow area, you can say ds by c into pt. It has to be multiplied by lb. So you will get width into length, you will get that flow area. That's the concept. Okay, so using this cross flow area, you can calculate the cell side mass velocity and also. So here they are using DE. That is another way, another complicated one in a cell side because D equivalent, you know how to calculate. That is flow area, 4 times of flow area into wetted perimeter. But in the case of cylinder bit exchanger, we have to different arrangement of tubes, equilateral, triangular pitch and square pitch. So if this is the square pitch, 4 times of free flow area. What is the flow area? This is the area available for flow. This is the portion available for liquid to flow, cross-sectional area available for flow. Okay. So what they have done? 4 times of flow area. How you calculate the free flow area? This is the square, correct? So PT square, correct? PT square. So then how will you calculate? You have to subtract these portions. So this is the D, correct? So this is all 4 equal to 1 cross-sectional area of 1 circle. That is pi by 4 D naught square. That is outer diameter. Okay. So what happens? 4 times of you can say PT square pi by 4 D square. I think this will not come here, correct? Sorry. So please correct this. This is wrong. This is PT square like this. PT square minus pi by 4 D naught square. That is the flow area. Wetted perimeter means these portions. 4 times of this 1 by 4 of pi D naught. Okay. So this is for 1 quarter circle. So 4 times you get 1 full circle, pi d naught. So what will happen? 4 by, you get 4 by 5, or you can say how you can modify this equation? 4 times of pt square minus pi by 4 times of d naught square. Okay. So pi by 4 you will get 0.785. 3.14 divided by 4. Okay, 3.14 divided by 4, you will get 0.785. Then what happens? So here you have to convert. This is PT square. So what happened here? Here you have 4. Okay, so 4 by 5. 4 divided by 5 will be 1.27. Okay, this is 1.27 by D naught. So here it is wrong. This is correct. Okay, PT square minus pi by 4 D naught square. That is the flow area available. So wetted perimeter is pi d naught. This is the D equivalent. Okay. For triangular pitch, the same way you can do. That is 4 times the flow area is cross sectional area of this triangle. That is 1 by 2 BH of BH minus pi by cross sectional area is this is 60 degree, 60 degree, 60 degree, 180 degree. So 1 by 2 of pi by 4 d naught square. Okay, so of BH, what is B? B is the PT. What is H? So this is your H, correct? This is PT by 2. This is your PT, correct? This is PT. So what would be this value? PT square, that is Pythagoras, you can use PT square minus PT square, P by 2 or P by PT square by 4, root of that value. So that is your H. Okay, so what will you get? So 3 by 4, root of 3 by 4 into PT. Okay, so that is your H. B is your PT. So PT into PT you will get PT square. Okay, or root of 0.75, root of 0.75 will be 0.87. Okay, so this is your 0.87. So this is the way you can calculate. So this is your area, triangular area minus half of this 3 quarters, three portions of this. That is 1 by 2 of this circle. Okay, 1 by 2 pi by 4 d naught square. So perimeter is similarly. So 60 degree, 60 degree, 60 degree. So 180 degree. So the perimeter is pi d naught by 2. So you can calculate the value. You will get 1.1 times of d naught pt square minus 0.970. So this is the way to calculate the D equivalent. Okay, I know you understand this. Do you have any doubt at this point? Hello? Anybody is there?
Sir, yes, sir.
So, any doubts at this point, especially
Sir,
in this?
I don't think there are
Okay.
any doubts. Please continue.
Okay. So this is the way that you can calculate the D equivalent. Once you calculate the D equivalent, you can substitute here to find out the Reynolds number. Okay. So cell side heat transfer coefficient. Once you calculate the Reynolds number, then again you have to fix the value of this baffle cut. So baffle cut range will be 15 to 45%. No, normally we will go for 20 to 25%. So you can fix the Reynolds number and corresponding JH you can calculate. Once you know the JH, you can calculate the value of cell side heat transfer coefficient. Or if your Reynolds number range is in this case, then you can use this equation also. This is another way, analytical equation. You can use this equation. If you don't have the chart, you can use this equation, or you can use this chart. Once you know the JH value, you can substitute and find out the Nusselt number. Then the pressure drop you have to calculate using this chart. Reynolds number, again you have to present the baffle cut. Then for a square and triangular arrangement, the same equation, same line you have to follow. Find out the JH factor. Once you know that, here you have to calculate the cell side pressure drop. So cell side pressure drop, when you compare this equation with the tube side pressure drop, only you have this additional terminology, that is L by B, LB. L is the tube length, LB is the baffle spacing. Okay, so what you will get? You will get number of baffles plus 1. This is your length, correct? So you have baffle, 1 baffle here. This is your tube sheet. So this is your first baffle, this is your second baffle, this is your third baffle, this is your fourth baffle. So what happens? This is your baffle spacing, correct? So this is L. So this is LB. Okay. So L by LB becomes 1, 2, 3, 4, 5. Number of baffles 1, 2, 3, 4. So what happens? NB plus 1. L by LB is nothing but NB plus 1. So you have to account this also, because here you have to account the pressure drop. Here you have to account the pressure drop. Here you have to account the pressure drop. Here you have to account. That's why you are multiplying this equation by L by LB. Okay. So another source of pressure drop is nozzle pressure drop. So inlet nozzle you can fix 1.5 times of velocity heads. Outlet nozzle you can fix it 0.5 times of velocity. Okay. So this is the way that you can calculate. You can do that design of cell and bead exit. So this is the simple algorithm for a cell and beat exchanger. First you have to define the duty, okay, then you have to make the energy balance to find out the unspecified flow rates or unknown temperatures, then collect the physical properties, the same thing, then assume the value of overall heat transfer coefficient, then decide the number of cell and tube passes, calculate the delta TLM, LMDD correction factor, okay, then delta TM. Then determine the heat transfer area, that is A naught is equal to Q by U delta T. Then decide the type, tube size, material layout. Then you have to assign that fluid, cell side fluid, tube side fluid, everything you have to done. Then calculate the number of tubes. Then calculate the cell diameter. Then up to this you have, correct? Up to this is sizing problem. Okay. Then since we all the sizing is being done based on the assumed value of U, okay, you have to validate that. So you have to estimate the tube side heat transfer coefficient, then decide the baffle spacing and estimate the cell side heat transfer coefficient, calculate the overall heat transfer coefficient, then calculate the difference. Or you can calculate the area instead of calculating the deviations using overall heat transfer coefficient. We can calculate the deviations using area also. Okay, so this can be 0 to 30%. If it is within this limit, you can estimate the tube side, cell side pressure drop. Then check, compare this pressure drop with the desired specification. If it is yes, then you can estimate the cost of the exchanger. Then again you satisfied, you can accept the design. Okay, so here if the area is requirement is very low, or you can say the deviations are higher, then what you should do? You have to modify your assumed value with the calculated value. Again you have to do the you have to reiterate this. Again you follow the same procedure. So if you are not satisfied at this point, if the pressure drop calculated is not within the specification, then what you should do? Again you have to change the layout of the exchange. It's not necessary that you have to adjust this. Okay. Otherwise, if your cost of the exchanger is higher side, what happened? What you should do? Again you have to adjust the specification. This is the step-by-step procedure of cell and repeat exchanger. Okay. So this is cell and repeat exchanger. Now we will solve some problems on cell and repeat exchanger. Okay. So we'll discuss some problems. If you have any clarification, you can clarify. Else we move to the problems. Okay. Shall we move to the problems? Okay. So we go to the problems. So do you have the soft copy of CR volume 6, all of you? Do you have the soft copy of CR volume 6?
No, sir.
Hello? Hello?
Sir, no, I don't think everyone has.
Am I audible?
Yes, sir.
Yeah, do you have the soft copy of Coulson Richardson volume 6?
Sir, I don't think everyone has. Some of us have it, some of us don't.
Okay, okay. No problem. I can share the link, you can download, or I can share the book itself. What do you want actually?
Sir, can you just upload the book to Teams? We can take it from there.
Yeah, okay. I upload the book. Okay, no issue. Okay. Otherwise, you can download the download from link also. That link also I can share. Okay. So today or tomorrow I do that. Okay.
Yes, sir.
Okay, sir.
Anshinath, when is our exam actually?
Sir, Tuesday we'll have from night 8 p.m. sir, 8 p.m. to 9:30.
Coming Tuesday?
Yes, sir.
8 to 9. Okay.
Yes. Two
Okay.
batches, sir.
2 batches. Yeah, correct. You have asked the 10th.
Sir, 10th means which day, sir?
10th also we can have. If you want, we can keep it.
We'll see in the CCM, sir. For 10th, I thought it was Ganesh Chaturthi, so we can't keep. But if
No
you're
issue. Then no problem. We can keep it on Tuesday. That is also okay for me. Anything is okay for me.
okay, sir. Then
Tuesday, Tuesday, like we can freeze it. Correct? Tuesday night, 8 to 9.
yes, sir.
Okay. Since
Okay,
you
sir.
all are busy with PPT. Correct?
Yes, sir.
Okay.
Sir, can
Okay.
you share the PPTs also, sir?
Yeah, today I share. No problem. Today, after
Okay,
this
sir.
class, I share it. Okay?
Okay, sir.
Okay. So we move to the problem. So anyway, I share, this is the example problem available in CR volume 6. Okay. Apart from that, we will see one more problem. Okay. Okay, so this is the problem. The problem is, design problem is like this. Design an exchanger to subcool condensate from a methanol condenser from 95 degrees centigrade to 40 degrees centigrade. This is the design problem. Okay. Design an exchanger to subcool condensate from a methanol condenser from 95 degrees centigrade to 40 degrees centigrade. Okay. So we have to subcool the condensate. Okay, it's not heat exchanger with phase change. That point. So you have to read the problem very carefully. Okay. So this is without phase change. Subcool condensate from a methanol condenser. So from 95 degrees centigrade to 40 degrees centigrade. So the condensate coming out from the methanol condenser is to be subcooled to 40 degrees centigrade. The inner temperature is given. Flow rate of methanol is given, that is 1 lakh kgs per hour. Sometimes they mention 100 tons per hour. Okay, 100 tons per hour, whatever may be this. Brackish water will be used as the coolant with the temperature rise from 25 degrees centigrade to 40 degrees centigrade. So brackish water will be used as the coolant with the temperature rise from 25 degrees centigrade to 40 degrees centigrade. So here we can select brackish water as the coolant, which is available in the process plant or very near to that. Okay. So the temperature conditions range also given. So it should not be heated up more than 40 degrees centigrade. Okay, this condition also given. Okay. So the given data are mass flow rate, inlet temperature of this condensate, outlet temperature of the condensate, then what is the cooling medium. Okay, coolant is given, coolant temperature conditions are also given. Okay, so here we have to do the thermal design of the exchanger. We are following the Kern method. Okay, whatever we have discussed. So since coolant is corrosive, we can assign to tube side. First allocation of fluids is being done. Then heat capacity of methanol properties you have to calculate 95 plus 40, that is 135 by 2. You can calculate around 67.5 or 68 degrees centigrade. We can calculate the properties of the fluid. So heat capacity of methanol at 67 degrees centigrade or 68 degrees centigrade, it is around 2.84 kilojoules per kg degree centigrade. Heat load is you have to calculate, this is the kgs per hour, no? So convert in terms of kgs per second, then specific heat kilojoules. Okay, then so heat load you can calculate, that is m Cp delta T. M is flow rate, mass flow rate. Okay, that is kgs per hour, no? Kgs per second you can convert. This is Cp value. This is the delta T, 95 minus 40. So you will get the value 4340. Okay, this is the heat load. Because the design problem is we have to cool the condensate. Okay, so that load has to be taken as the design load. Okay. So even the brackish water load you should not take. So this is the load that you have to take. Okay. The heat capacity of water 4.2 kilojoules per kg degree centigrade. Cooling water flow rate you can calculate. So heat gained by the brackish water is equal to heat loss by the condensate, methanol condensate. Okay. So this is Q by M. Sorry, Q by Cp delta T. 4340 divided by 4.2, 40 minus 25, you will get 68.9 kgs per second. This is the flow rate of your cooling water. Okay. So what is the flow rate of condensate? It is around 27.78. Okay. So this value is 27.78 kg per second. This is 68.9. How you know, or you can calculate. Okay. So then the second step is that you have to calculate the delta TLM. Okay. So 95 minus 40. What is the condition? 95 40 25 40. So the hot fluid is 95 to 40. Cold fluid is 25 to 40. So this is 25. This is 40. You can assume counter current flow. Okay, now what happens? Approach is almost 0, correct? 40 minus 40, almost 0. Okay. So what you can do? You can use one. You can start with 1-1 exchanger, or you can start with 1-2 exchanger. Whatever maybe. Here you can, if you start with a 1-1 exchanger, the FT will be 1. So LMTD you can calculate. That is 95 minus 40, 40 minus 25. Okay. So this is what is this value? This is around 55. 95 minus 40, 55. 40 minus 25, 15. So 15 by 55 by 15 is approximately 3 times. 4 15s are 60. So 3 times 3.67 times. Okay, 15 by 10 by 15, 3.67 times. So as per AMTD, LMTD thumb rule, we can go for LMTD. Otherwise, what will happen? 55 plus 15, 60, 70, 70 by 2, 35 degrees centigrade. But what do we get? Yes, for AMTD, the delta T value is 35 degrees centigrade. Here we get 31 degrees centigrade. So you can start with 1, 2. So if the number of passes, tube passes more than 1, what we should do? We should calculate capacity ratio and S value, effectiveness. Okay. So what is capacity ratio? 95 minus 40 divided by 40 minus 25, 3.67. S is the temperature, actual temperature rise of cooling water, 40 minus 25. The maximum possible is 95 minus 25. So this is your effectiveness. So you can use this equation. The FT value is 0.832, or you can use this chart. This is for 1-2 passes. So what is the value of S? X-axis 0.21. Here the R value is 3.67, but this case you have 2.534. So approximately you have to position this 3.67. So 3.67 will be like this, correct? So this length you have to find out. So you have to 3 to 4. What is the length? Proportionately you can position the point. This is point. Okay. So from here you can hit out, the value will be 0.85, approximately 0.85. Using the chart from the above equation, it will be 0.832. So please substitute the values in this equation and make a practice whether you can use this equation. Okay. So the value is 0.832. Once you know the value, then what you can select the value of U. Okay. So here methanol brackish water, correct? So what is this? Here river water, well water, sea water. This is the range. Okay. So on another side you have methanol. So methanol means you can mention this is the paraffins, or you can say light organics, whatever may be. Okay. So this is the range you can select this case. So within these, if you connect these 2 points, this is the range you will get, correct? So here 500 to this is actually 1, 2, 3, 4, 5. Okay, so 50. 550, 600, 650, up so 500 to 650 it goes. So you can select U value around 600 watt per meter square degree centigrade. Okay. So once we know the delta T, we know the U, we know the Q. So you have to calculate the area. That is the next step. So this is the provisional area. So this is the load. So this is the LMTD. 26, that is 31 into 0.85. That is 26. 31 into 0.85. That is 26.35. Your U value is assumed value is 600. So you get the provisional area. This is the area that we are providing for this exchanger to meet out the requirements. Correct? Now you have to choose the OD of the tube, ID of the tube, length of the tube, everything, material of construction, then corresponding value of thermal conductivity, everything you have to define. Because we have to calculate the number of tubes. So NT or area is equal to NT into pi by pi D naught L. So this is the heat transfer area, not cross sectional area. Okay. So NT you have. So we have three unknowns, correct? NT, D naught, L. So we have to define D naught and L, so that you can find out the NT value since A is known. Okay. So here L equal to 4.88 meter long. Okay. So approximately it is 16 feet. Okay, that's why. So it may be 8 feet, 10 feet, 12 feet, 16 feet or 20 feet. Here our initially calculations, we have selected these dimensions to decide the layer. Okay. So allowing tube sheet thickness, that is 5 mm, we can take. So effective length, L effective will be 4.83 meters, or you can take 4.88 meters also, that doesn't matter. So it won't change much. For example, this case for 4.88 divided by 4.83 is 1.01 times into 0.303. So your area will increase only 1%. So this 0.306 meter square you will get. So this last digit only the different in these two cases. Okay. So that also you can verify. Okay. So number of tubes. This is the area. So this is the heat transfer area of one tube. So total number of tubes divided by area of one tube. Sorry, total heat transfer area divided by area of one tube will give the number of tubes, 918 tubes. So what is the next step? We have to calculate the bundle diameter. Okay. So here it is being, we have to define what is the pitch, triangular pitch. So this is 1.25 times of diameter. So you, for two passes, for this combination, we have to find the value of K and N. Because NT is known, dB bundle diameter is equal to D naught NT by K over 1 by N. So we are using analytical equation. Or what you should do, this dB by bt you have to calculate, dB by bt. So dB bundle diameter we have to calculate dB by bt, that you don't know. Okay. So approximation you have to done. Okay. Then or you can use this tube sheet layout diagram. Sorry, tube count table you can go. Okay. Tube count table you can go. Okay. So you can calculate the ID of the cell. If you go tube count table, you can calculate the ID of the cell. Okay. So number of tubes, dB you can find out. dB is equal to 20, that is D naught. The number of tubes is 918. This K value for this combination is 0.249. N value is 2.207. Okay. So substitute all these things, you will get the bundle diameter. Okay. So kindly practice using calculator. You have to do this. Otherwise, it would be very difficult. Okay. In examinations, you will struggle to do these calculations. Okay. 918 divided by 0.249. So power 1 by 2.207. Okay, into 20, you will get 826.2, so approximately 826 mm. Then what we should do? We having bundle diameter, then we have to calculate the cell diameter. So cell diameter you have to use the clearance. So here it is being selected split ring floating head type is being selected. So this is the bundle diameter versus cell diameter minus bundle diameter, that's clearance. Okay, this is split ring. So this is 826. Draw the line at this point. Calculate the clearance at this point, 68 mm. Or you can do 826. No, you can do 640, 64 also. You can round up. 890. You can make it. Okay, whatever maybe you can round approximation. Okay, so here 894 mm. Okay, so if you use this tube count table, it would be around 863 or 914. The higher side you have to take. So take the tube count table, calculate, the value will be around 914 mm. So here you are getting 890 mm. So this is the range, correct? So average of this you will get approximately the same thing, 890. So 864 plus 914 divided by 2, you will get 890 approximately. Okay, the same thing. Okay, next thing is that, so now we know the layout of the exchanger. You know the bundle diameter, you know the tube diameter, you know the square pitch, you know, sorry, the triangular pitch dimensions, you know, length of the things, you know. So now you can do the approximation of your exchanger, approximate layout of the exchanger. So what we should do, we have to validate these sides. So go for tube side coefficient. Okay, so calculate the water mean temperature, 40 plus 25, 33 degrees centigrade. Tube cross sectional area, this is the ID. So cross sectional area means flow area, pi by 4 d square. This is the flow area. Okay, for one tube. So tubes per pass 459. So we calculated number of tubes 918. This is 459. So total flow area is per pass is 459 into 201 into 10 power minus 6. You are converting in terms of meter. So 10 power minus 6. So 1 mm is equal to 10 power minus 3 meters. Okay, so this is the total flow area per pass. Okay, then you can do the calculations, heat transfer coefficient calculation using two different things. You can use this equation especially proposed for water by Eagle and Ferguson, or you can use this equation also, Cped equation also. Okay, so here you can use this 4200, 1.35 T is the temperature. So temperature, average temperature you have to take, correct? Average is 33 degrees centigrade, you can take. Velocity you have to calculate. So you know the flow rate 68.9 kg per second. So you can calculate the mass velocity. That is flow area, correct? So kg per meter square second. So this is kg mass flow rate, kg per second divided by kg per meter square. So you will get the water mass velocity. The density of water at this temperature is 995 kg per meter cube. So water linear velocity is water mass velocity divided by density, 0.75 meter square. Substitute here because this velocity should be in meters per second. Temperature in degree centigrade is not convert in terms of Kelvin, that matters here. Okay, so if you use Kelvin, then value will be different. Okay. Then what is this? This is di, that should be in mm. Okay, that should be in mm, 16 mm. Okay, so this is the value of it. Or you can use Cped equation. Here you know you have to calculate Reynolds number, Prandtl number, mu by mu w. Okay, so this case we can neglect mu by mu w, that is approximately 1. So HI di by k is equal to this JH you have to calculate. To calculate the JH, you know the Reynolds number. So Reynolds number is dV rho by mu. So density is 995, velocity is 0.75. Anyway, this is in lower side. For water, it should be around 1.5 to 2.5 meters per second. Let's see what happened. Okay, so 0.75. This d is 16 into 10 power minus 3. This is your viscosity. Calculate. This is more than 4000. So it's turbulent flow. Okay, so you can use this equation, Cped equation. Okay, so that also verified at this point. Then calculate the Prandtl's number, 4.2 in 10 power 3. This is unit conversion, that is kilojoule is converted into joule. Then viscosity is 0.8 millinewton, 10 power minus 3 newton second per meter square. Thermal conductivity of water is 0.59. So you have to remember the thermal conductivity of water, 0.6, 0.62, 0.58, whatever may be. So you approximately it's 0.6 at atmospheric temperature. So Prandtl number value you should know. So this 10 power 3, 10 power minus 3 will make your Prandtl number. Sometimes you will get 5.7 into 10 power 3 if you don't do that proper unit conversion. So most of the people will commit mistake when you calculate the Prandtl number. Please remember, okay, whenever you are using viscosity, okay, whenever you are using Cp, you have to be very careful. Dimensional homogeneity you have to be checked, otherwise it would be incorrect. Okay, then you can check L by Di, that is 302. Okay, so calculate the value. Here your number is 14,000, correct? 14,900, 15,000. So here almost we no need to bother about this L by D because this is turbulent flow. Then you can use this chart and find out the value of JH. It is around 3.9 into 10 power minus 3. So it starts from 10 power minus 3. This is 10 power minus 2. This is 10 power minus 1. Here also you have to be careful. So this is 1 into 10 power minus 3. This is log flat. Okay. I hope you all know the use of log flat. Okay, because it you can for wide range of data you can accumulate in a single plot. So it starts from 10 to 10 power 6, 10 lakhs. Here also you can see 10 power minus 3 to 10 power minus 1. In ordinary graph that's not possible. Okay, so that's the advantage of log plot. So calculate the JH value. Okay, then substitute here, find out the heat transfer coefficient. Okay, so here H is JH is 3.9 10 power minus 3. Your Reynolds number is 14925. Prandtl number is 0.33, 5.7 power 0.33. This becomes 1 kF. That is thermal conductivity of the fluid 0.59. dA is the diameter of inner pipe, that is 16 10 power minus 3. This is 3812. Now you compare these two values. Almost same. Here 3852, here you have 3812. Okay, so you can take 3812. So now you move to cell side coefficient. Cell side means you have to define the baffle spacing. So you can start with 0.2 times of baffle spacing. Normally it would be 0.2 to 1 times of diameter of the cell. Correct? Okay. So 894 is the diameter of the cell. So 178 mm, Q pitch 1.25 times of D naught. Q pitch is 1.25 times of D naught. Cross flow area is PT minus D naught by PT into your DS into baffle spacing. I hope you understand the concept of cross flow area. Okay, this is your tube now. So this is center. Similarly, you have, if this is diameter, you have. So this is your DS, correct? So this is your PT. DS by PT will give the number of things, number of gaps into that is the clearance. Clearance is PT minus D naught. Okay. So DS by PT will give the number of gaps. Then you have to multiply by length. So length means baffle spacing, because each section you have to calculate. Baffle spacing you have to take. Okay. So this is baffle spacing. Okay. Then calculate the mass velocity. So what is this? This is the flow area. So we can calculate mass velocity kg per meter square second. Then equivalent diameter. This is triangular pitch. So you can use this equation. That is 1.1 times of 1.1 by D naught times of PT square minus 0.917 D naught square. So this is the equivalent diameter. So mean cell site temperature you can calculate. At this temperature you can calculate the properties. Okay. 750, density of methanol is 750 kg per meter cube. Viscosity is 0.34 centipoise. Heat capacity is 2.84 kilojoules per kg degree centigrade. Thermal conductivity is 0.19 watt per meter degree centigrade. Substitute Reynolds number, find out 36,700. Prandtl number is also 5.1. So these calculations you please perform. Okay, please check the values. Then what you should do? You have to calculate the heat transfer factor JH. Okay, here it is function of your baffle cut. Okay, so you have taken triangular pitch and assume the baffle cut 25%. For the Reynolds number 36,760. you can calculate the JH value, that is around 3.3 into 10 power minus 3. Okay. So without viscosity correction term, you can calculate the heat transfer coefficient, that is 2740. So now we are neglecting this viscosity correction factor. We are assuming this is mu by mu W is 1. So this is 1. Okay, so we have that. Now, or to account that, what you should do, you have to calculate the viscosity of the Celsius fluid at the wall temperature. How you can do that? This is the way to calculate the wall temperature. This is U T minus T. Okay, T is cell side bulk fluid temperature, small t is cube side bulk fluid temperature. So this is the heat transfer. Actual heat transfer takes place between hot fluid and cold fluid. So this is only cell side. Okay, so that is the heat transfer from bulk fluid to cell wall. Okay, so we have to calculate this TW. This is the way to calculate H naught TW minus T equal to U into T minus T. Okay, so mean temperature difference is 68 minus 33. So what is the equation? So U by H naught into delta T. This is your 35. So this is the average temperature, bulk fluid average temperature. What is the case? 90, 45. This is cell side fluid 95, 40. Sorry, 95, 40. So this is 25, 40. Correct. So this is the average temperature 33. So here 135, around 68. So this is the actual approximate delta T between cell side fluid and tube side fluid, 35 degrees centigrade. Okay, so you can calculate the temperature U by H naught into delta T, that is U is 600, H naught we have calculated, correct, without this temperature correction factor, viscosity correction factor. So 35, that is 8 degrees centigrade. So TW minus T is 8 degrees centigrade. TW is the wall temperature, T is the average cell side average temperature, correct. So this is so 68 wall temperature, here it is 33. So wall temperature you have to calculate. So this is the wall temperature. So you, this is small t, correct, small t only. U by H naught, T is your value 68, this is 33. So this is your T wall minus. So what happens? So this is equal to 8. Okay. Sorry, you can say TW minus T, you can say, or T minus TW, you can say. This is another way, T minus TW. The equation will be T minus TW into H naught. Because the profile you know, no, this is a hot side, sorry, cell side fluid temperature. This is tube side fluid temperature. This is the wall. So temperature profile will be like this. Okay. So this can be 60 degrees centigrade. So viscosity of methanol you have to calculate. That is 0.37 centipoise. So mu is we have calculated already. That is around 0.34. This mu W is 0.37. So approximately 0.99. So variation is not that much significant. So approximately if you take power 0.44, this becomes 1. Okay. So what we should do, we have to calculate the overall heat transfer coefficient. So the conductive cupro nickel is being selected as the material of construction of the tube. So from this you can calculate the conductivity, that is 45 watt per meter degree centigrade. So the equation is 1 by U naught. This is the generalized equation used to calculate the overall heat transfer coefficient. So this is your cell side heat transfer coefficient. This is dirt factor. This is conductive resistance. This is area correction factor. This is dirt factor of tube side fluid. This is area correction factor. This is your tube side heat transfer coefficient. Okay. So for fouling factors, you have to select from table 12.2 of CR volume 6. Sea water and light hydrocarbons, the coefficient will be around this value. So substitute this. This is calculated 2740. So light hydrocarbon, which is 5000. Then this is 20 into this is D naught ln of 20 by 16, 2 into kW. This is the unit conversion. kW is 45. Here it has taken 50. Okay. Plus this is the value, 20 by 16 into 1 by 3000. This is dirt factor you can take. Then this is the area correction factor. This is the heat transfer coefficient of water. So what is the U value? It is 738 watt per meter square. So individually you can calculate. So you can see whichever contributes. Okay. So what is the problem here? It is around 3000. It is 4000. So this dirt factor, this one will minimize the value. I think this is the major resistance here. Okay, this is U calculated. So calculate the provisional area. This is being calculated already. So the required area is 226.2 meter square. So we have given more area. So now you can calculate what is the 738 minus 600 divided by so approximately deviation is around 20%. Or you can calculate the area 278. Required is 226. So 278 divided by 226.2. It is 1.22 times. So area provisional by area required is 278 divided by 226. So this is the area required for the defined case. So 226. Okay. So approximately it is 1.22 times. So it can be, this ratio can be 1.1 to 1.2 times. Almost same. So we are satisfied with the area. So now we have to check the pressure drop in cell side and tube side. Okay. So tube side pressure drop you can take. So calculate the Reynolds number we know, that is 14925. Then calculate the JF value. From the chart, substitute the JF value. You can calculate the delta P in tube side. So number of passes is 2. 8 JF. JF is from a chart 4.3 10 power minus 3. So L is 4.83 in 10 power 3 mm, because 16 is your dA in mm. This mu by mu W we have taken as 1. This is your major loss plus 2.5 times of this velocity here, 995 into 0.75 square by 2. Okay. So this is your pressure drop, 1.1 psi, very small. Okay. So what you can do, because your velocity is also 0.75, 75 meters per second now. So you can increase the number of tube passes. You can increase to 4. So if you increase the 4, what will happen? So this becomes 1.5. So now you see the pressure drop, 1.5 times ut square, 1.5 power. So what happened? Previous case it is 0.75 square, correct? So 1.1 psi or 7.2 into 1.5 square divided by this 0.75 square. So 28.8 kilopascal it will come. But you have to check the heat transfer coefficient also. If you change the velocity, you have to check the heat transfer coefficient also. Okay. Cell side pressure drop, calculate the linear velocity. Maximum can be 1. Here it's 1.16, no issue. So calculate the delta PS. So here this L by LB is the baffle spacing. Okay. So 8 times. This is the factor for the Reynolds number. This. Then your diameter is 894. D equivalent is 14.4 mm. L by LB. This L is the effective tube length. This is the baffle spacing. So rho U is, this becomes 1. So rho 750 into 1.16 square by 2. So this is the, so here it is higher side. So pressure drop 39 psi, you see, because this velocity is more. What you should do? So only thing is that you can adjust the baffle spacing. Okay, so cell side pressure drop is higher side. So doubling the pitch. So you can increase the baffle pitch. So what happened? The pressure drop is approximately 1 by 2 square. Okay, because delta PS is 272 here kilopascal. So as per this equation, this becomes this is what happened. The velocity is U square, baffle pitch is off. So just this is 1 by 2 square, correct? So that reduces the pressure drop by a factor 1 by 2 whole square. So this becomes what? 68. So it is in acceptable. But you have to check the heat transfer coefficient. Heat transfer coefficient comes down 1573. Okay, so this is the relationship. So we have discussed, no, if you change the velocity, it reflect on your pressure drop and also your heat transfer coefficient. Anyway, in this case, pressure drop is on higher side. So by adjusting the velocity, we can brought down. Okay. So correspondingly, we have to check the heat transfer coefficient. So for this, using this simple case, because baffle speed is doubled, no, so velocity will be off. So previously 1.16, 1.16 divided by 2, that would be the velocity. So this is 1 by 2 power 0.8. Reynolds number power 0.8 is proportional to US power 0.8. So 1 by velocity becomes half. So 1 by 2 power 0.8 into 2, because all other things are same. Okay, this is approximately, or you can do by procedure also, because you can check whether what is the change in JH, because your Reynolds number will also change, no. So if you change the velocity, what happened? dV rho by mu, no. So your velocity Reynolds number becomes double. If Reynolds number becomes double, you have to see the corresponding JH. That also matters. Okay, this is on approximation. Okay, so you can actually calculate this, and now you can calculate the overall heat transfer coefficient. That is 615. Whatever, this is also in higher side. So calculate the U naught. Then again find out the area. Then check the new area, corrected area, that is 271. Then this is also very close to 1. But so already we have provided 278. So 278 is greater than 271. 278 divided by 271. So 1.02 times. Okay. So this is the way to do the design of heat exchanger. If you have any doubts, please ask. Hello?
Sir, yes, sir.
No doubts.
Shall we wind up or?
Yes, sir. Yes, sir. We can wind up, sir.
So,
So,
please.
excuse me, sir.
Yes, yes.
So, what will be the pattern of the CT?
How about no? So it would be objective, true or false, objective, multiple choice question.
So, there won't be numericals?
Numericals will be there.
Like, so, like this type of long numericals won't be there, right?
Not long. For your action 2 minutes calculation, like that I will ask.
Oh, okay.
So you should be thorough with the design calculation. Accordingly, I will ask the question. Okay. So this is the procedure. Okay. So in this design procedure, I will ask questions.
Okay.
And other topics, whatever I have covered. Okay.
Sir, will there be any time allotted for each question during the test?
Yeah. Each question I will allot time based on the length of the what is the steps that are required. So length of the your procedure, the time will be allotted. If the procedure is very long, then I will give more time. Okay. So any other doubts?
Okay, sir. That's it, I think.
Okay. So I share the book and other material. Okay. So you can take it from Teams. Okay.
Okay, sir.
Thank you. Thank you all.
Thank you, sir.
Thank you, sir.
Thank you.